Okay, let's unpack this. You've dropped a fascinating stat of material on us today, sitting right at this incredible intersection of human language, how our brains grapple with it, and the bleeding edge of artificial intelligence.
It's a really rich convergence, isn't it? And the core question driving this deep dive, it's super compelling. Can these sophisticated language models we're building in AI, particularly models like the Transformer that have, revolutionized the field, can they actually serve as tools to understand something fundamental about human cognition?
Right, specifically how our brains handle memory when we're processing sentences.
Exactly, making sense of sentences in real time, because just reading words isn't enough, like you said.
Yeah, our brain is constantly having to look back, pull information from earlier in the sentence, figure out which noun that pronoun refers to, or which subject matches this verb, even across layers of embedded clauses. It's a dynamic memory game.
Absolutely. And the material you shared centers around a recent study that tackles this directly. They use the transformer architecture, but introduce a significant innovation they call transformer grammar, or TG.
TG, okay.
And by comparing TG to a standard transformer and using a clever metric tied to the AI's internal workings, they investigate this very idea of memory retrieval during human sentence processing.
So consider this deep dive your targeted shortcut. We're sifting through the research to extract the most important, most surprising insights from this complex intersection of linguistics, psychology, and AI, really focusing on the academic contributions this work makes.
Think of it as zeroing in on the aha moments presented in this study, sort of bypassing some of the dense academic preamble.
Perfect. Let's ground this first by talking about the human side. How has psycholinguistics historically thought about how we process sentences?
Well, traditionally, there have been two major camps, though they aren't mutually exclusive. One focuses on expectation, how we predict what words are likely to come next, and how processing difficulty arises when our predictions are violated.
Right, that's often measured via surprisal.
Exactly. Like if I say, the programmer wrote some very long socks.
Uh-huh. My brain stumbles because socks wasn't expected after lunch.
Exactly. But the other major angle, and the one central to this deep dive, is memory-based theories. These propose that sentence understanding heavily relies on actively retrieving previously encountered information from memory as new words come in.
So as I read, my brain is kind of casting around in its recent memory of the sentence.
Precisely. Cue-based retrieval theory is a prominent example. It suggests that cues from the current word, like a verb needing a subject, prompt your brain to search your working memory buffer of the sentence so far for an element with the matching features.
And here's where it gets really interesting and honestly pretty relatable for anyone who's ever gotten tripped up by a complicated sentence. This retrieval process isn't always smooth, is it?
It is definitely not. One of the key phenomena psycholinguists study is interference. Retrieval becomes harder, you experience increased processing difficulty, which we can measure, for instance, through slower reading times.
Okay.
When there are other elements in your memory that share relevant features with the item you're trying to retrieve, they interfere with finding the right match.
The example from the source makes this crystal clear. The worker was surprised that the resident who said that the warehouse was dangerous was complaining.
Right. When your brain hits was complaining, it needs to find its subject. The correct subject is resident. But the word warehouse appeared recently in that embedded clause, and crucially, it also has subject-like features in its own context.
Ah, it's a distractor.
It's a distractor. Your brain has to sort through potentially relevant items in memory, and warehouse interferes with retrieving resident. Humans reliably read words like complaining slower in these interference-heavy structures compared to simpler sentences. That slowdown is the empirical signature of retrieval interference.
Okay, so we have this well-established psycholinguistic idea of memory retrieval and interference in sentence processing. Now, how do these massive AI models, specifically transformers, connect to this?
This is where the innovation the source discusses comes into play. The incredible success of transformer models in tasks like translation and text generation is largely attributed to their attention mechanism.
Right.
And researchers are now asking if this purely engineering-driven mechanism might offer a computational window into that human memory retrieval process.
The attention mechanism is basically the model deciding, for each word it's processing, which previous words in the input sequence are most relevant, right? It's like the model looking back at its memory of the text so far and assigning different weights of importance.
Yes, that's a great way to put it. It's weighting its access to the preceding context. The hypothesis is that this weighting process in the AI is analogous to how our brain's memory retrieval mechanism weighs potential candidates when searching memory.
So how do you take that internal AI process, how its attention is distributed, and link it quantitatively to human processing difficulty like interference.
That requires a linking hypothesis, exactly what the source proposes, using normalized attention entropy, or NAE.
NAE, okay.
This metric is designed to quantify how diffuse or spread out the model's attention is over the preceding tokens. The academic idea here, building on prior work, is that if the model's attention is scattered across many previous words, perhaps because several seem somewhat relevant or interfere with pinpointing the single most relevant one, that high entropy or diffuseness in the AI might reflect the retrieval interference a human experiences. It's a computational attempt to capture that cognitive clutter.
NAE sounds like a clever way to measure the messiness of the AI's internal search, hoping that maps onto our brain's messy search.
That's the intuition behind the linking hypothesis, yes. Now, the study goes a crucial step further by comparing different types of AI models using this NAE metric, asking what kind of internal representations yield NAE that best matches human data.
And this is where the two main models in the study come in.
Precisely. First, you have the vanilla transformer. This is the standard, widely used architecture. It's incredibly powerful, but it primarily operates on the input as a linear sequence of tokens words or subwords.
Right.
While it implicitly learns relationships between tokens, it doesn't build or use an explicit hierarchical syntactic parse tree in its core process.
It largely sees the dog chased the cat as just 5 words in a line.
Essentially, yes. The key innovation highlighted in the source is the second model, the transformer grammar, or TG. This model is fundamentally different because it's explicitly designed to jointly process the sequence of tokens and simultaneously generate their corresponding syntactic structure.
Ah, okay. So as it reads the dog chased the cat, it's not just seeing tokens, it's actively building the noun phrase, the dog, and the verb phrase, chase the cat, and seeing how they fit together.
Exactly. It's learning the grammar as it goes. And TG has a really novel mechanism that's central to this study's academic contribution: compose attention.
Compose attention.
Yeah. When TG identifies that it has completed a syntactic constituent, like a noun phrase or a verb phrase, what the source calls a closed phrase, it uses this special compose attention step.
What does that do?
It takes the individual token representations within that completed phrase and computes a single unified vector representation for the entire phrase as a unit. This is a major difference from the vanilla transformer.
Interesting.
It allows subsequent processing steps and, crucially, subsequent attention lookups, which is where NAE is calculated, to refer back to this structured phrase-level representation in memory, not just the individual tokens that made it up.
Okay, I think I get it. The vanilla model's memory contains just a list of ingredients, like the words. But the TG model, using compose, can create and store the mixed batter, the finished phrase unit, and refer back to that instead of just the individual ingredients.
That's a good analogy for the difference in representation. And this ability to represent and potentially retrieve phrase-level units is what makes TG a more plausible model for syntax-aware processing.
So the central academic question of this study becomes, if NAE calculated from attention models human memory retrieval, does NAE from a model that only sees tokens, vanilla transformer, better predict human interference effects, or does NAE from a model that builds and uses syntactic structures, transformer grammar, do a better job?
Right. Which kind of memory representation seems more plausible for the human brain? That's the precise inquiry.
Okay.
To investigate this, they trained both a vanilla transformer and a transformer grammar model. Then they processed sentences from the natural stories corpus through both models.
The natural stories corpus is perfect for this, right? It's real language, but designed to include lots of those tricky sentence structures known to cause human interference, and it comes with detailed human self-paced reading time data.
It's an excellent dataset for linking computational models to human processing difficulty. They calculated the NAE from both models for each word position in the sentences. Then, using standard psycholinguistic statistical methods, linear mixed effects models. They tested how well the NAE from each model predicted the human reading times, while controlling for all the other usual suspects known to affect reading speed, like how common the word is, its length, and even how surprising the word was according to the model's own predictions.
And a quick note on methodology. For calculating TG's NAE based on structure, they assumed the globally correct syntactic structure for each sentence, treating it like a perfect oracle.
Yes, that simplifies things, but allows a direct test of the value of perfect structural representations for predicting human data. It provides a clear upper bound on how well structure-based retrieval could predict human data if the brain had perfect parsing.
Got it. All right, the moment of truth. What do they find when they crunch in the numbers?
The results are quite striking and represent a significant academic finding. First, validating the general approach, they found that NAE from the vanilla transformer did significantly predict human reading times.
Okay, so the basic idea holds up even for a simple sequence model.
It does. This confirms that there is some relationship between token-level attention diffuseness and human processing difficulty, lending support to the idea that attention might generally model retrieval. But here's the key reveal and the main academic contribution. The NAE calculated from the transformer grammar, TG, showed substantially stronger predictive power for human reading times compared to the vanilla transformer's NAE.
Wow.
The difference was quite large statistically.
So the messiness in the AI that's aware of sentence structure lines up much better with where humans actually slow down.
Precisely. This strongly suggests that memory retrieval based on syntactic representations plays a more dominant and critical role in human sentence processing than retrieval based solely on the linear sequence of tokens. This is powerful evidence for the psychological reality and importance of structured representations in memory during language comprehension.
But it's not just one system winning outright, is it? They found something even more nuanced.
That's right, and this might be the most crucial insight of the entire study. Using likelihood ratio tests to compare statistical models, they found that a model including both the MAE from TG and the NAE from the vanilla transformer was significantly better at predicting reading times than a model using either one alone.
So it's not an either-or, we're using both kinds of memory.
Absolutely not. This finding provides strong empirical support for the idea that human sentence processing involves dual memory representations. We seem to have one system that stores and retrieves information based on hierarchical syntactic structure, like TG does, and another system that operates more on the linear sequence of tokens or their semantic associations, like the vanilla transformer.
Okay.
The attention mechanism in this view might be the general retrieval algorithm that our brain uses to access information stored in both kinds of representations. This dual system view is a central hypothesis this work supports.
Okay, that makes intuitive sense. We process the words themselves, but also how they fit together grammatically. Did they look closer to see if these systems handle different things, maybe different kinds of words?
They did, using an analysis broken down by part of speech, POS tags. This provided more granular evidence for the complementary nature of the dual systems.
What did they find there?
TG's NAE was particularly strong at predicting reading times for verbs.
Verbs. Okay, that makes sense.
Verbs are often the linguistic triggers for retrieving arguments, subjects, objects, etc., which is fundamentally a syntax-heavy process. When you hit a verb, your brain needs to pull the correct noun that performs the action from your memory of the sentence structure.
And the vanilla transformer, where was its NAE better?
Its NAE, operating purely on the token sequence, showed better predictive power for nouns.
Nouns. Interesting.
Retrieval triggered by nouns might involve more associative processes based on the word itself or its linear position, perhaps related to semantic memory or discourse context, less tied to strict grammatical roles than verb-argument retrieval. This difference in which parts of speech each NAE best predicted really bolsters the dual system interpretation.
Fascinating. And they also specifically tested whether TG's advantage was just from having any syntax or from that special compose mechanism you described, where it treats phrases as units.
Yes, this was an important academic control to pinpoint the source of TG's power. They created a variant model, TG-comp, which also processes syntactic structure, but without the compose feature that creates single vector representations for completed phrases.
Right, the mixed batter representation we talked about. And how did TG-comp stack up?
Well, TG-comp's NAE did predict reading times better than the vanilla transformer, confirming that simply considering syntax helps. The full TG with the compose mechanism significantly outperformed TG-comp, especially, again, for verbs.
So treating that completed phrase, the blue bird, as a single unit in memory rather than just remembering the individual words within it is crucial for capturing the human-like retrieval.
That's the strong implication. It suggests that the specific way TG creates and represents these closed phrases in memory using compose attention aligns particularly well with how humans seem to retrieve information for syntax-driven processes. This novel mechanism, developed in AI, seems to mirror a key aspect of human cognitive representation for language.
That's a really specific point of contact between the AI architecture and potential brain mechanisms. Now, finally, one more key academic point they addressed. Is NAE really capturing interference, or is it just a proxy for simpler effects like decay?
Ah, yes, the interference versus decay question.
Right, the idea that information just fades from memory over distance or time in the sentence.
This is a critical distinction in psycholinguistics and a significant contribution of this study. Psycholinguists have models for decay effects, like category locality theory, CLT, which measures processing difficulty based on factors like the linear distance between words.
Okay.
It's been harder to get a broad measure of interference, especially in natural text. By comparing TG's NAE with CLT, they found that both NAE and CLT made independent, significant contributions to predicting human reading times.
Meaning NAE is capturing something distinct from just distance or decay.
Exactly. This provides strong empirical evidence that NAE is indeed quantifying interference, the difficulty caused by distractor sharing features, which is separate from decay effects. This offers researchers a promising new tool, particularly NAE from a syntax-aware model, to measure interference effects in natural language processing, addressing a long-standing challenge in the field.
That's a powerful new lens to look through. Stepping back, the source mentions this research operates at the algorithmic level in David Marr's framework for understanding complex systems. Can you quickly explain what that means in this context?
Sure. David Marr proposed 3 levels for understanding a system like vision or language. The computational level asks what the system does and why, what problem is it solving.
Like prediction?
Right. The algorithmic level asks how it does it, what representations does it use, and what algorithms manipulate those representations. And the implementational level asks where and how it's physically realized, what neural circuits are involved.
And a lot of language model work predicting human data stays at the computational level, right? Like saying surprisal captures the computational problem of prediction.
Precisely. This study, by contrast, is delving into the algorithmic level. It's asking about the nature of the representations used in memory. Are they token-based or structure-based? And investigating attention as a potential algorithm for retrieval from those representations.
It's trying to model the actual steps.
Exactly. It's trying to build models of the processing steps our brains might actually be using. This is a deeper, more ambitious level of cognitive modeling.
So what are the big takeaways from this deep dive? What are the implications for AI and for our understanding of the human mind?
Well, first, it strongly suggests that to build AI models that are better cognitive models of human language processing, we need to explicitly incorporate syntactic structure, not just rely on models that process linear sequences of tokens.
The vanilla approach, while impressive, isn't the full story for how humans do it.
Right. Second, this study provides some of the strongest evidence yet for the idea that our brains likely use at least 2 distinct types of memory representations simultaneously when processing sentences. One based on hierarchical syntactic structure, and another based on the sequence of words or their statistical semantic properties.
The dual memory revelation.
Exactly. And finally, it provides researchers with NAE, particularly NAE derived from syntax-aware models like TG, as a potentially powerful new tool for empirically quantifying interference effects in natural language states, addressing a persistent challenge in psycholinguistics research.
It feels like a genuinely exciting moment where AI isn't just a tool for building technology, but a tool for doing cognitive science.
It absolutely is. Using AI as a test bed for psychological theories allows us to formalize hypotheses about representations and algorithms in a way that wasn't previously possible. The attention mechanism and engineering invention becomes a computational hypothesis about human memory retrieval.
So what stands out most to you after going through this material? Is it that attention in AI might mirror our own memory, the compelling evidence for those dual memory systems in our brains, or perhaps the cleverness of transformer grammar and its compose attention specifically capturing that structure-based retrieval?
That's a tough choice. For me, I think the most academically significant point is the rigorous empirical evidence for the dual memory representation hypothesis, derived from comparing these computationally explicit models against human behavioral data.
Right.
And the fact that NAE provides a concrete way to measure interference, something notoriously difficult to do reliably in natural text, is a major methodological step forward for psycholinguistics.
Yeah, that does seem huge. And that leads to a fascinating final question to leave you thinking about. If our brain is constantly accessing information from both a structure-based memory system and a token-based system using something like attention, what happens when those two systems give conflicting signals or suggest different interpretations? How do we navigate or resolve that internal disagreement?
That is a fantastic question and definitely ripe for future investigation.
Indeed. Thanks for joining us on this deep dive into the surprising connections between cutting-edge AI, the attention mechanism, and the fundamental ways our human brains handle memory during language processing.